So in this lecture, we will be learning about the concept of stress. So basically, in stress, we generally focus on um, the nature of stress. Secondly, we focus on distribution of stress. And the other factor which we are going to focus is the magnitude of stress, and the last factor, that is the maximum value of the stress. Maximum value of the stress. Okay, so now suppose there is a cylindrical workpiece looking something like this. Now it is subjected to some axial load of magnitude P. Now we are going to take some element here at this cross section. So if we are going to zoom this element, so it looks something like this thing. So this is the taken element which we have zoomed further. Now suppose there is some alpha molecule on left hand side, alpha molecule here, and on right hand side there is a beta molecule which is attached together by a certain bonding, which can be ionic or covalent bonding. So this is a bond between alpha and beta molecule. So the main thing I'm going to want to convey is that so let me first draw some schematic diagram here. Okay, so this is the cylindrical bar, and axial load P is acting, which is tensile in nature, and here is the here is the alpha molecule, and here is the beta molecule, and so this load P tries to pull the alpha molecule, and beta molecule tries to pull back alpha molecule. So this beta molecule tries to pull back this alpha molecule by offering some internal resistance. So let me cut this portion, and now let me plot the cutted portion like this portion. So it will be looking something like this. Yeah. So the internal force will look something like this. So this is the internal force, and this is the load P. So this is the internal resistance which is offered by the beta molecule to oppose the movement of alpha molecule in the direction of the applied load. So during equilibrium condition, summation of force in the x direction equal to 0. That is x-axis. This is the x-axis basically. So we can say that P is equal to the total internal resisting force, total internal resisting force. So here the total internal resistance force is equal to sigma into the cross-sectional area, that is A. So internal resisting force, internal resisting force developing at unit area, is known, like we can define this as a stress which is represented by sigma symbol, which is equal to P by A. So now let's focus on the another concept, that is Hooke's law. So let me erase this thing first. Okay, cool. So now let's talk about the Hooke's law. So suppose there is any cylindrical cross-sectional piece or specimen without any load. So when we are going to subject the this cross section to some load, then we are going to get somewhat this thing. This is the final configuration, and this is the initial configuration, and this is the final configuration. So it is subjected to some load P. So we can observe that firstly at the initial configuration, the initial length was, we can take it as L, and for final configuration, that is when it is subjected to the load, then the length changes to then this length changes to L plus del L. So we can plot a graph which looks something like this thing. So on x-axis there is the strain, that is change in length upon original length. So this is the delta L. So strain is strain we can define as change in length upon original length. So on x-axis there is a strain and on y-axis there is a stress. So the plot looks something like this. Yeah, so it looks something like this. So we can see that it is the equation of slope of the line, which is y equal to mx. So similarly, sigma is equal to E multiplied by strain. So we can say that here slope is the constant, that is m and e. So we can say that it is a material property. So it is a material property. Okay. So we can write sigma is equal to P upon A. So we can write as we know that sigma is equal to which is equal to Young's modulus multiplied by the strain. So we can further write it as E. Here the strain is change in length upon original length. So delta L upon L. So this is the axial loading equation. So this is the axial loading equation. So this is the axial loading equation. Now we have talked about the nature of the stress and the magnitude of the stress. So now let's talk about the distribution of the stress. So let me clear this thing first. Okay, now let's talk about the distribution of stress. Distribution of stress. So now let's take the same portion which we have cut from the cylindrical cross section for calculating and establishing the relationship between the applied load and internal force. So it looks something like this thing. So this is the cut portion of the specimen on which the load P is applied, and this is the internal resistance to the applied load. So basically it shows the distribution. So we can say that there is a uniform distribution of stress at one given cross section. Now let's understand the another concept. So here is the specimen, like take some specimen. Some rectangular specimen here. Now, now consider the two different locations. Like take this as x1 position and this as a x2 position. So this is the reference point. So this is the just take from here to here and from here to here. So the main takeaway from this thing is that stress varies with distance x. So maybe sigma x1 is equal to sigma x2, or sigma x1 is not equal to sigma x2. So it is not fixed, because it just generally varies with the distance x. Now another thing you should note that another thing you should keep in mind that let me first clear this. Okay. So another thing is that let me plot the diagram. This is the rectangular cross section, okay, and it is subjected to some load P. Now let's see how the stress distribution. So basically, the distribution means the distribution means how any quantity is varying at all possible points. So near the concentrated load, the distribution looks something like this. So near the concentrated load, that is at this point, the load distribution, the stress distribution looks something like this thing. And so this is near the concentrated load, that is near to the concentrated load P. So this just the distribution looks something like this, and away from the load it has uniform distribution. So uniform distribution away from the concentrated concentrated load. So this is the main concept and this is the main takeaway from this lecture.